so I have it. There are 10. We just took 6, so we're on 7. 8's pretty long, but it's fun. 9 is Taylor's series. 10 is short. It's polar parametric and vector. No. Outreach is after AP exams happen. All right. Let's see. Who's not here today? Just Kian? All right. So what I would like to do first is round 2 review. A couple comments on the test. This test, which happens every year, but it was a little more obvious this time, to use the word we're going to be using on the test and further on, the test scores are what I would call diverging right now, meaning the high scores are staying high, the low scores are creeping a little bit lower than I would like. So I would encourage you guys to do some review. I was a little unnerved to see some blank questions just because it doesn't give me a whole lot of direction to give you other than just like a highlight that you need to do this question again. If you have concerns about the test and you want to go over questions, I literally am usually alone here in the morning. I also can make time for you at other times of the day. I just want to reiterate that because I don't want you to feel uncomfortable. So if you're feeling like you need to review, just know, I'm just reminding you yet again, I am available in person, via email. I would like to help. That being said, the partial fractions questions look really good. I liked those. The trig questions look pretty good as well when I was flipping through those notes. So I thought you guys did a good job on that. The ones that were a little bit messy for everyone were kind of these bottom 3, which makes sense. It was towards the end of the unit. This one's a little bit creepy. I thought this was a kind of reach question anyway. So if you thought that one was hard, good. That was one of the harder questions. I will say a couple of people did get to the end of it, which I was pretty impressed by. This was the question that looked like the table. That was supposed to be easy, but I think some people got freaked out when they saw the table, and one of my 7th block wanted to go over that. So I just put that there. I'm going to give you guys a solid bit of time to go through this. Another comment, a bunch of people chose the right methods on these 2, but had some weird stuff towards the end of the question. So what I'm going to do is I'm going to give you this piece of paper, going to give you a solid amount of time to work. I'm happy to go over all of these, but as I'm asking you questions, I want you to be participatory because I don't want to just do the questions on the test for you. I already know that I can do them. I want to know if you've learned anything. So feel free to bebop around. Don't feel like you have to do the first question first. If number 4 was a question that you did not like on the test, which is probably most of you, because it was one of the harder ones, start at number 4. That's totally fine. Let's see. I'm going to start with 15 minutes. It's probably not enough, but we're going to start there and see where we're at. So. If anyone wants to come in the morning and ask me like what they should study for the test, I'm cool with that too. I'm not here to make it a mystery. Oh, how are you doing? All right. You like move it? It's like looking right at me. All right. Let's start with 15. Let's see how we're doing. I do have a full answer key, so if you're stuck anywhere, let me know.
I don't. This is what makes like yeah.
Oh, she did.
I was even there for a while. I like that you went from day back to Monday. This is one that I just. I was doing like supposed to do like a thing. Oh my gosh, it's art. The big thing is I would, oh my gosh. So I did an. I was literally saying, I asked her, like, I was like, oh, I don't think we have to go over the and everybody else. And I was like, oh, I know I did. She's like, this is I know, I was doing it, and I was set up myself, and then I just left it anyway. And I was like, I absolutely the problem is. He usually goes to DX. He usually goes to LMI. Are you supposed to do it? One divided by x is x. No, 1 x times p. And x I think there's a you're going to do it the way I did it, the way I did it. Oh, I think yeah. I was with those places for not. I'm trying to find the notes for. Alright, so X over, that'd be great idea. These are all
If you're looking for some of the more specific integral rules, you want this one.
Yeah, okay. So remember you said you can draw things? No, you should be the numbers. No, but I know. So for this one, how do I? All right, so that doesn't match. Yeah. 1/2 I know. I guess this part. Yeah, I was coming out the bottom. Hold up. Did the 3x? Not this one because the down here. Oh, and then so I would just do yeah. Then you can do well, you can go the X minus 1. Yeah, that was good. I don't want to do how long is when you multiply no, I know. One over x is No.
But other than that.
Oh, I thought you were confused about.
I'm just trying to.
Oh,
Now you are there also. No, I know there's a good bit, but I felt something like you can't go to next. What about the people?
I never did
Not times to divide by your new power.
That's all I can.
But I still have the.
Why was the front page there? So, this is question number 2. Yeah, it is.
Yeah, if you have, the trig function will kind of never get any simpler as we take a derivative, but x squared, we'll take a derivative of 2x, like it's getting simpler. We're actually gonna have to do it twice for this one to get the x squared down to a number. So actually that one, if you remember the tabular method, that one might work really well.
I can't find one that has that ability to specifically find that.
I got 1/3 here.
Right.
Provided like I was
Then I would plug in your bounds. Okay, so now, if I would just. This thing is very bad. It's wrong.
I don't know. It's like I'm on the test.
If I can't agree with that,
That's fine.
There's no way. Yeah, no, a bunch of people did it, I think everyone was just overwhelmed with like all of the methods we've learned.
So
you can't make this. I wouldn't, because that derivative is never gonna get as simpler. Oh. I would make
Yeah, yeah.
So because there's two x's.
My sine goes to 1/3 x sine 3x plus cos 3x.
That'll be on the x. I thought
Oh, I would definitely download this first time.
Oh, you did.
Yes, I would agree. The only thing I don't agree with
Okay.
So that one, I agree, iteration by person twice, that would be a good candidate for that popular method. You wanted to see that, it would be good for like the people. So the reason we're gonna have to do it twice is because as here is their product. So a couple reasons you can deal with it, since this is a negative, you could take the two, just one third, put them all here, and do the second iteration first, put it in a big set of words. Behind that, that would probably work really well. And then I would build the same theme as this, and have my accent all over yeah. So to integrate in that step, we're gonna have to
Start off for.
Wait, I love that one.
You plugged in the sound. Now we're just gonna vibe it out.
So we had some of these two guys, and you wanna make sure this one stays A. Yeah. But think of like, if you can think of the graph of regular things, that one is where that graph has its vertical asymptote, so they're kind of being rotated. So actually, the negative is in the asymptote is down, and the edge is higher, so it's opposite, that's up.
Okay, for info, I have to say that this is what you said no, and then went back.
So it's like, no, very, thanks. So that one was a lot of 23. Oh, other than that.
Or you could put it on the.
Oh, wait. No, so we have, my mom realized what it has. You can put it wherever you want. Still have it
And I always hear the other, because I roll it, like,
So options there, I think what I would do is keep the two in the one third.
yeah.
And put them at the negative sign, when I integrate
Similar
this
to that
part,
one.
you do it.
But it's just not, it's multiplied by the rest of it.
Over A, A,
No.
Oh, you can do that in the number, the other side is one.
Oh, yeah.
You have to divide that.
Well, that's supposed to be like, yeah, because like, wait a minute, bro, are you doing that? I don't know.
Why don't you go back?
They have got, look at the. Yeah, I mean, I don't know.
Yeah.
I always down to one.
Think about it. I do. And then if I'm going to integrate.
That's what I did.
It is.
I'm so good.
So I've heard all the same things. You do that. Yeah. Well, if the limit is equal to 0, it doesn't have to.
And then we have to put like the limits. Then,
The quantity is.
Nice.
It really is. That's not one of your questions on the test.
I definitely love this pointless type
You have to do the one to ten. Honestly, you know,
I also know how to do this.
Yeah.
Right.
Thank you. That means so much.
But do. Oh, yeah.
That's what I think too, but like, things I thought I would never say. What is it? Review? You did, you do.
What a sentence.
What is it?
Only as a math teacher.
But you know what the cool part is? We knew exactly what we were doing.
Exactly. Only as a, I'm that smart.
Oh, yeah, I see what I did. I did.
I gave up. Just getting to these parts. This is gonna get us.
I can't even remember how to do it. You said that last. So if you have like last year, it's here.
I think this is how we are.
Oh, I do. Oh, yeah. And then I did. After that, I was I was just
To be fair, I just did that. It was
You don't have to do. Oh,
Oh, so we did this.
Oh, for number 4? Yeah, I don't really know Well.
All right, proposal. That was 15 minutes plus a couple. Thoughts on like 5 to 8 more, and then I just start going over.
Yeah.
Where are we in that range? 5 to 8? 8-ish?
I'm gonna have no time to teach today. I'm gonna go 7, lucky 7. Then I start talking.
So at the end of the 7, you don't necessarily have to be done, but have looked at all the questions. Yes.
Am I right?
Yeah.
Oh my god.
How did question? How did you solve?
Wait,
Yeah. No, I got that.
Okay, so if one just decided not to.
Okay, let's go. Let's go.
Should I have 3 colors? Imagine if you use another color.
Oh, wait, no, I think that's such a. I like put it.
Yes, you could.
Interesting.
I remember this was the big word. What if I got further than a year? I would go far, but I don't want to.
Yeah, I would rather.
We just wonder. I don't know. Oh, now I would call it.
No, look, no, look, there's only one extra one.
Yeah, I understand.
So you can take.
Yeah, but now it's cool.
Don't have to be plugging your bounds, and that's where you will mess up.
Oh, like.
Do you? This is a tool, by the way.
Oh, okay. I like that. So
Yeah.
what I would do is honestly, they will work is already created. So I would do this.
Oh, right.
That's where you're gonna do this. Kind of like this guy. You don't know that. I can help you with. You're gonna have top bound and bottom bound.
Gosh.
Oh, I'm gonna do it yet. Oh, it's kind of. Oh. I always box man. Like my work is so messy. Oh, yeah. One plus honestly, we don't have it now.
Like a basic you guys are losing your position, right? We set it up.
You don't like your. That's not legal.
Yeah, it does.
For power, one,
This way, I think we're-
So Serena, your favorite function? Yes, but you have a negative infinite, right? So where is that going?
This. And then this all is two. You have-
40 negative. Oh my
Yeah,
god.
right. And then you have the 6 there.
So wait, you plug your mountain into it?
Oh,
my
bound
So that's just one square. You think it's one square. One is.
So.
It's one square. And one is like.
But you're like
This, a lot of people are trying to integrate doing it. I would do instead of trying to do X surface.
I think it's
And one is all of your.
that is the possibility.
That will make sure you don't credit it. So I would make that two-thirds and you're just integrating it. It makes it a lot cleaner to like focus on things.
I know.
And here, I don't think we need to up here, so I can just go through, I have X times this, that does need integration by parts, so I barely touch that. And here, I have number times that, I want all of that, so it's just very. It also cleans it up a little bit, makes it more pointed.
One of them is conference. That was the final city college. Danny is over here. Yes. I thought it was a lot of higher numbers.
So it's gonna go.
Yeah, that's what I'm saying. Oh. Yeah, but negative. But it's negative. Yeah. Weird. I don't know. Or I know. Oh. This should have written.
No, you never mind. Oh, we're one over X times X plus
Well, I wrote it down here. I like.
Yeah. Gosh darn it. Yeah, it works out.
All right.
Are you more like, right?
And then
All right, I'm gonna do these questions really quick. Again, as I'm going through, the minute you stop answering my questions, I got some rotations to do. So I'm gonna make some comments as we move forward. There were specific reasons I asked these questions. The first one had to do with the Voodoo part. So do you guys agree integration by parts? All right, how did we know? All right, we have multiple x's being multiplied. I'm actually not going to do u is x. I'm going to do u is natural log of x. Some of you chose to integrate natural log and you got 1 over x. That's the derivative of natural log. So maybe flip-flop right there. dv then is x dx v 1/2 x squared. All right, so if I'm doing my uv minus the integral of b du. This was the spot that got really messy. A bunch of people tried to integrate x squared and 1 over x separately. The reason we can't do that is because when we have two things that have x together being multiplied, we either need to simplify or we need to use integration by parts. Here, I would argue simplifying is better. What is x squared times 1 over x? X. So yeah, I'm gonna have the half. I chose to move it out front here, but I have to simplify this before I start integrating again. So 1/2 x squared. Make sure this set of x's and this set of x's cannot combine. So I usually just throw mine out front. This guy integrated is 1/2 x squared. So with that 1/2, I'm getting 1/4 x squared, of course, plus c. All right, this is that. So I have to simplify it before I integrate it. And I pull the 1/2 out. Yeah. What? Where? Oh, yeah.
When you move that 1/2,
Yeah. All right. As long as it's mathematically equivalent to that final answer, I'm good. So if it's unmultiplied or whatever, I don't care. It needs to be mathematically equivalent to that. That's probably fine. All right. So next one, also integration by parts. Here I want to choose the x's as my u because I never want to choose something whose derivative looks kind of exactly like he does. So cosine, terrible choice because cosine derivative is, it's just going to sine cosine its way forever. Here, some people missed the u sub on this guy. The u sub on that guy. What number is that going to chuck in front of my sign? A 1/3. Some people said something equivalent to 3. So you're going to have some number adjustments. U is 3x, du 3dx divided by the 3. So we're going to do integration by parts. We got u, v. I'm going to kind of clean up as I go. Minus integral of v du. Now, this is where things got a little bit creepy because some people, again, tried to integrate these two things separately. We're not allowed to do that. What I would do, and I've been talking a lot to, if anyone knows Nina from my other class, she agreed with me. If you're getting confused, a lot of the time, moving your constants to the front of your integral really helps your eyeball, at least. So what I'm going to do is take this 1/3 and this 2, and I'm going to put them all out here. Since I'm not making you simplify, you can use parentheses to your advantage. Now, a lot of people tried, again, to integrate these things separately. That's not okay. They both have an x in them. I need another integration by parts. So I'm going to set up with the same general scheme as the first one, where I'm using u as my x stuff and my dv as my trig stuff. Here, if I integrate, I have negative cosine 3x, but I also need to 1/3 again. So that has to happen multiple times. You could certainly move the x. I would leave the dx at the back because that's kind of the closing parentheses for my integral. But yes, if that makes you happier, absolutely. Because in our integration by parts formula, so we're not substituting for the stuff we see in the integral, our integration by parts formula wants what du equals, whereas like in u sub, we're trying to match what we see in the integral to sub in for the stuff with dx. I can give a better explanation for that later if you'd like. You kind of want to mirror whatever you did here. You don't want it to ever be a trig function. All right, so what's up? Yeah, absolutely. All right, so I'm going to keep the 2/3. Since integration by parts has 2 terms, I'm going to open up a big set of parentheses here. I'm going to do u, v, using the second set, minus the integral of v du. Kind of simplifying as I'm going. So here I'm going to have a lot of terms. I'm just going to keep my parentheses going and making sure I'm keeping that first term. So minus 2/3. This guy's going to stay exactly the same. And when I integrate this last piece again, still need this u sub. So I'm going to have plus 1/9 from another 1/3 sine of 3x. It literally doesn't matter where you put the c. You can put it inside the parentheses, outside the parentheses. If it's getting multiplied by a number, it's still a constant, so it doesn't matter. So if you're looking at yours, your middle term should have plus 2/9 x, and your last term should have minus 2/27 if you have it all multiplied out. Zach? No. Connor? Yep. Yeah, so it is massive. If you hate what I just did, take a look at tabular method, that last question from the integration by parts on our notes where we made the table. That's a really good option for this question. If you want to go over it, see me in the morning or see me later. Yeah. It needs another use of. I was just pointing that out. Why are we screaming in the bathroom? It's usually the boys' bathroom, though. Thanks, Michael. You can take the 9.5 if you want. All right, number 3, improper integrals. These ones, the notation is pretty darn important. Here we need our limits. We're going to limit out the bottom bound. Now, I like to use A. You can use any letter you want that's not just X. All right, this integral does not have a natural log in it. What favorite function is coming to town? Arctangent. If we have a squared in the bottom, no x's in the top, arctangent. So we're doing arctangent here. U is x, A is 1. Hint, A was not 1 on the test, so I'm going to go ahead and just plug in my bounds right away because I'm feeling comfortable with that. And let's see if we remember any of our arctangent values, because I did want you to evaluate these. What is arctangent of 1? Equivalently, where is tangent 1? Pi/4. As we go to negative infinity, negative pi/2. Just for fun, as we go to positive infinity, pi/2. Arctangent of 0. Don't think too hard. It's 0. So I get 3 pi/4. So this is what our graph looks like. This y value is pi/2. This is negative pi/2. Answer. That is in just our arctangent formula. So whatever the u is, it's whatever I did to square that. 1/2, so positive 1/2 plus 1/4. 2 halves plus 1/4, or 2/4 plus 1/4 is 3/4. All right, choose me a color. Purple. All right, limit again. Ugh, why did it get all thin and squiggly? Yeah. All right, another improper integral. I tried to give you a hint by making this have this in the denominator. Some people took my hint. So integral of this, again, we got to remember our rules. 1 over natural log of 3, 3 to the x plus b. You could do u sub on this, but the u, there's no constants to keep track of, so I just treated x plus b like its own thing. Here, my bounds are going to be from A to 2. Nope, no plus c since I have bounds. Here, plugging in 2, I've got 3 to the 2 plus b over natural log of 3 minus 3 to the a plus b over natural log of 3. This guy, that second term, is the only one that has an a in it, so it's the only one that really is going to change with regard to this limit. So the first term is going to stay as is. The question is, where does the second term go? Really, we're looking at this piece, the 3 to the a, because the plus b is not doing too much since I'm plugging in negative infinity. If we're talking 3 to the negative infinity, where is that trending towards? 0, because it's looking like 1 over 3 to the infinity. That's what our negative exponent is doing. That is trending towards 0. Now notice this little work that I'm doing is kind of off to the side scratch work. we are trying to avoid actually plugging in infinity in our work. So notice none of the places where I have equal signs have that. So all of that term is 0. All right, setting it equal to the thing they said it was equal to. Thoughts on solving this? What should I do? Ooh, interesting. I'm going to get rid of the natural log of 3's first, then I'm going to go there. You said 2 plus b equals 3. How are you getting that? Yeah, 3 to the third is 27, so you can set these exponents equal to each other. Pretty cool algebra trick, and I get b equals 1. You could also just try to plug stuff in and see if it works. Hey, Sean, you had your hand up? Oh, you were just going to help? Cool, thank you. All right, last one. I think the table just scared us. This is actually one of the easier questions on the test. Thoughts on method? Hello? Integration by parts. All right, what's u? So dv is g prime of x dx. That makes vg du dx. Now, the bounds were the interesting part in this question. So I'm going to do my integration by parts, and we're going to talk very specifically about the bounds. So when we do bounds in this question, we have a problem. The g of x, do we know like the antiderivative, the function that is the integral of g of x? No. We do know a very specific thing about the integral of g of x dx, and that is from 1 to 2, I'm going to get 6. So I would really like to put bounds on this guy, but that means I have to put bounds on the front end of this as well. This is already integrated though, so I'm going to put bounds on like this. Some people tried to put them on at the end, which made you subtract this too many times, if that makes sense. Because when I go and plug in my bounds, I only need to do top bound minus bottom bound for this first set of stuff. So I'm going to do 2 times g of 2, which is 3, minus 1 times g of 1, which is 5. That's for this term. For this term, the second term, that's just equal to 6. So I'm just going to subtract 6 there. We've got 6 at the front end, minus 6 at the back end, so our middle term survives negative. That is the answer. Okay, so that one, though it made you interact with things that were like a table or whatever, that question is probably one of the easier ones on the test. Right. All right, so recommendations. This document, if you're looking to look at it later, you didn't get all of it written down or you just want to revisit, is posted in our Unit 6 folder on OneNote. You're more than welcome to look at it later. If you are feeling nervous about a different question, or maybe you're looking at these and you want a different explanation, you want a different version of it to practice, email, morning, anytime. Just let me know what I can do to help you out. For some people, the cosine sine trig one was good. For some people, that secant tangent one might deserve a second look. That one I think you could do both ways, but one of the ways is definitely easier than the other one. So there we go. Are we feeling a little bit better? All right, cool. We will round 2 at the beginning of next class. All right, are we ready to rotate? Yeah, you'll start. All right, let me find a picture of what we're doing today. All right, should we take a break right now before we roll into notes? All right. While I pass out notes and get everything ready to go, you guys may take your break. Take 4. I will be back to teach you in 4.
As long as you do it on both.
As long as I had a couple of you where it made it so like it's not answer, that's not okay.
But I usually don't bring any pictures. I'm just
Oh, boy. Yeah, my thoughts, my thing about it. Don't look at the ground.
Oh, no.
I mean, I can see
We
it.
should skip driving.
I don't know, that's the funny thing.
The one class where you actually win the light of there's an actual answer.
Mr. Moon does literally nothing on him last week. That's such a meme.
Dude, I took AP games like a week.
Yeah.
If they ever explain and
Dude, Vince did nothing.
Oh, they explained it.
Really?
I don't know.
I don't get it.
With like health insurance? I went and we had to choose new health insurance. And I went and asked my dad, I was like, what do I do? He's like, I don't know.
They're just like, get health insurance.
Yeah,
That was the
They
thing.
don't tell you there's so many choices.
No,
That's all they said.
Okay, well, we have three.
Yeah, that's so true. They're just like, you should get it.
All right, let me change this graph to the first graph that we're doing.
And then they explain what a debit card is.
What?
We're talking about your old last name and your last name.
Oh, I know. I didn't. It got closer though. Last class it said AB Calc and said Boston. I got a step closer this time to.
We're getting there.
It's just I edit the notes and then I forget to edit the header.
When did you go to, when you married?
2017.
Yeah, Jason had you as
Yeah, so did my sister. Do you remember my sister?
Yeah, she was the first one who showed me the way to remember the trig derivative.
Oh, cool. Oh, wait, yeah, you can.
Oh.
So if you take the derivative of tangent, it's secant squared. If you take the derivative of secant, it's secant tangent. I should teach this to you guys.
Yeah.
I never remember it this way. I just memorize it.
Why did I
So it's tangent is
This is the way I think of it.
Secant is cosecant cotangent.
You just have to remember how to like
My
write
brain
that.
is
And then you
exploding.
choose secant, secant, tangent, cosecant, cosecant, cotangent. You just remember this one's negative.
Tangent is
It's a lot of things to remember though.
Tangent is secant squared.
No one ever just makes flashcards and memorizes things anymore. See, our teachers, when I was in school, our teachers never were like, here's a cutesy way to remember things. Like when I do quotient rule in my head, I say bottom derivative of the top minus top derivative of the bottom over bottom squared. There's no one. Yeah, like that's so much cuter. The scenes.
Anything that's like,
Not for these ones, for derivatives. All right, let's rotate. So I'm gonna kind of not follow the directions since our review took a little bit of time today. We're gonna do, instead of find the volume, just to save a little bit of time, are you okay if I change the directions, not on the paper, obviously, because I already printed it. Can we do a setup but do not evaluate today? Yep. That cool? All right, I have the answers if you want them, so I can tell you the numerical ones, but just to save some time typing it in. So here's the first problem we're going to be doing. I'm going to draw you a picture in a second, but the idea is that we're going to take a region in the plane, and instead of like the last time we learned, build up some cross sections on it, we're going to take that region and we're going to rotate it around some different lines. Some promises I'll make to you. I will never rotate it around a line that is not horizontal or vertical. Me and Aiden Freeze tried to figure out how that would work last year. We decided definitely outside the scope of our class, starts talking about like different angles. It gets really, really weird. So it will always be a horizontal or vertical line. The cool part is if you did this last year in your class, which most of you probably should have at least looked at this, we're going to learn a different way to rotate next class where we won't kind of rotate this. It'll be cooler. And the cool part is we'll choose between those methods. But today, we're talking disk method. I can demonstrate both. So these are the first two questions we're going to do. Here's the first one. This would be an example of what I would call disk method. All right. We're taking this line, we're rotating it around y equals 1, so that region, we're kind of making a ball-shaped thing. The next one is going to have us go around y equals 0. This is called washer method. What do you think the difference is? There's a hole in the middle. Now, for both of these, I'm going to try to rotate so we can see. What cross section does it look like we're using? Like, what is the shape of the thing? The shape, if we looked at it from the side. All right, a donut, but do you agree you see circles? Okay, so we got either a big circle and a small circle, or if I go back to the y equals 1, hold on, we just got one circle. So we need to know the area formula for a circle. It is? Good. Pi r squared is going to be all over the place today. So let's start. I'm going to draw a picture, start to draw some of the notation and the verbiage I'm going to use. And I'm going to add the notes to our thing, volume by washer method. All right. In a second, I'm going to draw a picture at the top there. I will preface the picture by saying I'm just going to draw two random curves. You may think they're pretty. I am not thinking of specific functions or anything. I'm just drawing something that will help me draw. This is just going to be a generic picture so we can talk about some of the verbiage I'm going to use today. So washer method will be subtracting 2 pi r squared from each other, but I'm going to mirror what I did last time where I kind of did an area formula first and a volume formula second to really segment my decision-making processes, if you will. So going to draw two random curves to give you an idea of what we're doing. Here is random curve number 1. Random curve number 2. You can draw anything you want as long as they only intersect in two places, and one is firmly the top function, one is firmly the bottom function. I just like the way that one looks. It kind of looks like a bird. See? All right. Cool. We are going to be rotating around a line just to make this example a little bit spicier. I'm going to make the axis of rotation not the x-axis. A lot of the time when we do these questions, the axis will be the x or y axis, which makes this this process a little bit easier, but we're not just doing the x or y axis. So for this guy, does anyone think if I take this region and rotate it around that line, do you think there will be a hole there, or do you think we will have like just a straight up disc going around? There's gonna be a big old hole. How can I tell? Yeah, this bottom part that's closer to the axis of rotation is not touching the axis of rotation at all. So I'm gonna have a big old hole here. So I am going to talk about two different, excuse me if I say the word radiuses today and not like radii like a fancy person, but we're going to talk about two radiuses today, a big one and a small one. And just like I hopefully talked about last time, I taught this to my BC class, my 7th block yesterday, so excuse me if I'm not saying things correctly. While I can draw the discs and washers, at the very least, I would like you to draw your big and small radiuses in, so you can kind of see what we're doing. We're going to do a lot of top minus bottom stuff again. If you like drawing things, you can try to draw these like cross-sectional things, but it gets a little bit weirder. But that's kind of the washer that we're working with. I don't think it's super helpful to draw those some of the time, so a lot of the time you'll just see me draw this. One thing I do want you to notice is we're never really dealing with the distance between the two curves. It's always the distance between a curve and the axis of rotation. So pretty much never, unlike last time, are we going to subtract the two functions from each other. We're going to be doing a top minus bottom with the farthest away curve in the axis of rotation and then the closest curve in the axis of rotation. So if you're ever kind of subtracting both of your functions from each other, probably not going to have a good time. I also may sometimes draw this shape. That is not a G. That's like a rotation sign. So just if you see that, it's not a weird G. I'm just saying, hey, I'm rotating around this line. So let's go ahead and I'm going to do two questions that correspond to the graph that we saw. So I'll kind of be flipping back and forth so we can visualize a little bit. Again, when we do these questions, we want to make sure we draw our region in the plane before we get started. So we're going to have this 2 minus x squared. That's a parabola, goes through 2 on the y-axis, facing down because of the negative. And then g of x equals 1 is y equals 1. That was that horizontal line that we saw. So we're going to be rotating around that line. Now, an underappreciated step in all of this is to really make sure you know which region you're rotating. Because if we start rotating a different region than we are supposed to, our stuff is going to go super wacky immediately. So just to be clear, we are doing this region. Everyone cool with that? That kind of semicircle looking thing? All right. Now, is this one going to have a circle and a hole cut out of it, or is it just going to be a disc? It's just going to be a disc. Notice this region is touching the axis of rotation the entire time we are rotating. So as we rotate, we are going to be touching. All right, example. I know this doesn't look like the semicircle, but function, axis of rotation. Oh my God. Is there a hole? No, because we are touching the axis of rotation the entire time. Thank you. So this guy, our representative, oh, it's going to hate it because I'm going to touch it. Okay, so this is going to do this. Oh, no. Oh, no. It's going to do this. Whee! All right, so, all right, I will try. Yeah, so there's going to be a lot more choices in this because there's a lot more situations based on where everything is oriented. All right, so let's go ahead. Everyone's cool if I just use 1 pi r squared. We just got the one disk. So again, just like we did with cross sections, I'm going to set up an area formula and then transfer into volume. If you're starting to get good at this and you want to do all of the volume all at once, you do you. I like to separate my decisions. So I've established 1 circle, 1 pi r squared. Now I have to figure out what my r is going to be. Theme, top minus bottom. I'm going from my function down to my axis of rotation. Again, I'm choosing anywhere in the region to draw that line. There's no sense of like why I chose the right or the left. I'm just in that region, and this is my r. What is my top function right here? 2 minus x squared, or my f of x. What is my bottom function right here? 1. Which could be g of x. So I could have written f of x minus g of x. I'm just using the functions here. All right. Now I'm going to transfer to my volume by placing this into my integral. Essentially, an integral is going to add a dimension for us. So we're going from an area to a volume. Now, personally for me, I like shoving the pi out in front of my integral. But just remember, we're using pi here because we're dealing with circles. So if you go back and do cross sections questions, make sure you're not just like adding a pi willy-nilly. You have to make sure you're using appropriate shapes. And for me, I'm going to try to simplify a little bit. So I'm going to take this 2 at the front and the -1 at the back and subtract them. I was talking to my 7th block a lot yesterday about what kinds of questions you might have to integrate by hand on a test. This is kind of like a borderline one because I would have to FOIL out that 1 minus x squared. I'm going to get a lot of fractions. So most of this test, if not all of it, is going to be calculator friendly or set up but do not evaluate. And that's kind of reflected on the AP test as well. These get really gross really fast. So you're not going to have to integrate a lot by hand. I am, though, going to need some bounds. How can we find the bounds? Okay, so we need as far left and as far right. So I need these intersection points. How can I find the intersection points of two things? I could set them equal to each other. So 2 minus x squared equals 1. Let me subtract 1 and add x squared. And I have a plus or minus. So I think I'm going from -1 up to 1. Now, pretend we put this into a calculator and we get 3.351. That seem like an okay answer? Why do you like it? Positive. That region, not that big, so 3 short. If I got 60, a little nervous. If I got 0.2, a little nervous. Yep, so for most of these, we're going to calculate. All right, so today the notes are set up where we're going to take one region and we're going to rotate it around a lot of lines. So I'm going to take this same region, and now instead of rotating it around this line, we're going to rotate it around this line. We already saw one big difference. What is one big difference between rotating around this line versus this line? There's going to be a big old hole in the middle. So I am not just going to have 1 pi r squared. I'm going to have a pi r squared minus another pi r squared for the whole. I unfortunately do not have this for that, but someone wants to make me one. All right, so just to reiterate that difference, we got, instead of this is the question we just did. Whoa, that is not what I wanted to do. Or was that 0? Here we go. So this was the question that we just did, and I will post these online if you want to play with them. I think they're very soothing to watch. We are going to rotate around the line y equals 0, which is the x-axis. So notice we are now probably going to get a much bigger volume because we've got this space inside, but it's kind of extending here. We've got this like cool bracelet looking thing. All right. So first difference. I'm going to quick sketch again just so I can see it. Whee. Whee. I can now label these because I know the intersection points now. But I got 2 radii that I have to figure out. I got this big radius here, but I've also got the small radius. When I say small radius, I'm meaning the radius of the hole in the middle of that guy. So for my area, I have to have a pi. That's not what? It's such weird noises. So we got a pi big R squared minus a pi little r squared. That bathroom is just the worst. All right, big R. So that pink radius, what is my top function? F of x, which is 2 minus x squared, is my parabola. What is my bottom function? Is it this g of x? Is that where the pink line goes down to? So, oh, sorry. For our bottom of this radius here, do you guys agree with me? We're going all the way down to the axis of rotation. So what number should I subtract here? 0. Now, that might annoy some of you. You are almost always going to see me write -0 because I'm reminding myself to check if there's a different axis. So I write a lot more than probably some of you will. And you do you. That's for me making sure I'm checking. How did I spell axis? Ooh. So I'm going from top function down to bottom. And that bottom is our axis of rotation, which is y equals 0. All right, let's see if we got our little radius. We got pi, little radius. 1 is the top, 0 is the bottom. Okay. Yeah, sorry, Connor. All right. Now we're changing to volume. Again, I like to take, in this case, both of these pies, chuck them out front. All right. For the first guy, I'm not going to FOIL this out. I'm just going to leave it squared. Personally, for me, the 1 minus 0 squared, I'm just going to write -1. Thinking of like plugging into the calculator, it's nice if you have it simplified. If you don't like that, just don't. And then thoughts on bounds? Do we like the ones we used before? Same bounds. So like cross sections, the bounds are really determined by the region. Unlike cross sections, changing the line of rotation is really going to do a ton to change kind of the innards, our integrand. A lot is going to change based on the line that we're using. So what I'd like to do next is take one different region, a little bit more complicated, and we're going to rotate it around 3 different lines. I want you to start looking for patterns, what things stay the same, what things are different, what things are a little bit tricky that we might want to look out for. This region is one we use with the cross sections. It's a very popular region. Do you remember what it looks like? Yeah, it's the leafy boy. It looks kind of like this. Anyone remember where the 2 intersection points were? Just me and Connor doing notes. I know, you did like this unit a lot last year. I like the look of this unit. It's just very fun and thrilling. All right, I'm going to draw some pictures. So first question we're going to do is we're going to rotate it around the x-axis. So let me run you through the choices I usually run through in my head. First choice, hole or no hole? Should we check it on Desmond? It's a cone hole. That's all right. Yeah. Hold on. Let me grab my perspective dot. Wee. Wee. All right. So what do we think?
There is only.
No.
If we change the perspective, it's like a little bowl.
All right.
It's like a bowl. Yeah, it's like a bowl.
Okay, so the reason you guys are getting confused, the answer is there is definitely a hole in there. The reason you're getting confused, and I know why, is at the origin. At the origin, I agree. It's touching the bottom. Is it touching the bottom, the axis of rotation, the entire time? No. We'll talk about the x equals 0 and why it's going to remedy itself, but you want that thing to be flush against the axis the entire time if you're going to say no hole. Yeah, so if I had an example of no hole, would be this. So notice when it comes back around, that thing is flush against the axis like this. If I open it up, that thing's going to be solid the entire time. If there is any space in between, we're going to have to remedy that. If it's, yes, so this is like a bowl. We'll talk about why the x equals 0 is going to remedy itself in a second. You may be able to see why, but it will work itself out. So let's talk about here. We have big radius, small radius. So big R, little r. Again, I like to write these out. Pi r squared minus pi r squared. So big radius. We're talking top minus bottom. What is this top function up here? Square root of x. And we're going all the way down to our axis of rotation, 0. For our little radius, we're going from this function, which I believe is x squared, all the way down to the axis, 0. Again, I use my area formula as a place to remember things. So that's why I'm going to write the minus zeros every time, even though I know they're redundant and I know they don't need to be there. The area I'm going to let be messy, and I'm going to clean up as I go to volume. I'm going to factor that pi out. And I'm going to clean up a little because I'm planning to plug this into my calculator. This would be a good example of one where I could expect you to integrate it by hand because the square root of x squared is x. X squared squared is x to the fourth. So that's a pretty easy one to integrate by hand. Yes, you'll end up with fifths, or fifths scary, not really. Glaringly missing are my bounds. Thoughts? 0 to 1. Just checking, is that this 0 to 1 or this 0 to 1? This 0 to 1. Remember, you can take your line and move it back and forth with your pencil in the same orientation. What? Mm-hmm. Left to right or bottom to top. Mm-hmm. All right, let's adjust. Let's adjust. I'm going to take this and I'm rotate it around a different line. Are we all cool with the first one? Super cool? Wow. Oh. All right. Y equals -2. Do you guys agree with me? That's about right here. All right. So these are my new radii. This is hole or no hole? Yeah, a bigger hole. Great. Pi squared minus pi squared. All right. Thoughts on the big radius? What's going to change about it? All right, the -0 is going to change, right? The square root of x is still on the top. What is that -0 going to turn into? All right, +2. I'm going to write -2 just for the sake of my notes. But I will change that to +2 in a second. What about the small radius? X squared minus -2 or +2. All right, volume, going to factor that pi out. Going to simplify a little bit, mostly just the square root of x +2. This would have to be FOILed out. So this is probably a good example of one that I would not expect you to integrate by hand. We have to FOIL out both of those combined if there are any like terms. I don't even think there would be, maybe the 4s. But it would be pretty nasty. Bounds still 0 to 1. Yep, bounds are reliant on that radius. All right, let's get spicy. Yeah. How do I get the bounds? Easy way, take your pencil, put it on one of these vertical lines. How far left can you go and stay in the region? How far right can you go and stay in the region? All right. Yes, before we get spicy. That's the bottom. All right. Reason we're getting spicy. Where is y equals 7? Above this region. Things get a little weird. Not that weird, just a little. A little. All right. Hole or no hole? Hole. We've definitely got some space between our region and the axis of rotation. So I've got 2 different pi r squareds. Now, big radius. This is a super vague question, but I'm wondering if I can get a specific answer out of you. Anyone notice something weird about the big radius and small radius? Connor. Yeah, so does everyone notice kind of the farthest away function is switching? Here, when we were talking about an axis for rotation that was below, our farthest away function was square root of x, whereas here, our farthest away function is x squared. Now, if we mess that up, it's actually going to kind of not be too scary of a thing because you'd actually get exactly the negative answer of what you should be getting. So the actually evaluating and getting that negative answer gives us a lot of good information. So let's talk about big radius. Anyone know what two things you would be subtracting? All right, I'm going to do 7 minus x squared just because I'm going to go literal top minus bottom. Technically, you would be fine because we're squaring it, but we're going to do a method later on next class called shell method, where the order will matter because we won't be squaring it. So I would highly recommend trying to actually do top minus bottom. Little radius, what are your thoughts? Perfect. All right, as I transition to volume, I'm going to factor out the pi. Nothing really to simplify here because I'd have to FOIL out. That would not be something I'd be doing for just giggles. Thoughts on bounds? 0 to 1. So if you're noticing, the bounds are super consistent as far as the region goes. So if you do get like a full free response on this, where you're dealing with one region, make sure those bounds are good at the beginning of the question. All right, I'm going to try to start. We don't have a notes check today, so I'm just going to try to start doing these last three. Might go a little bit quicker. What we're going to do is we're going to do essentially the same thing, but we're going to work in terms of y. Mason. Yeah, are you wondering if we could go in terms of y? Absolutely. Great question. Great segue. Let's do it. I can. So instead of rotating kind of vertically, what we're going to do next is rotate horizontally around a vertical line. So while cross sections was really specific where it was like perpendicular to the x-axis and you could use x, here you want to think about like what axis are you rotating perpendicular to, I guess. So if you're rotating perpendicular to the x-axis, you can still use x. So any horizontal rotation is good, and then anything where we're kind of rotating. All right, let's draw a picture. Square root of x, that looks like this, right? Ish. X equals 4 looks like this. 4. Just because I said we're working in terms of y, let's grab this y value. If that's 4 comma what is on this graph? Cool. Convincing. All right, y equals 0 is the x-axis. So again, we want to be very clear with ourselves. I'm going to erase this in a second, but everyone agree we're working with this piece right here? Yeah. All right, first thing, y-axis. All right, notice if we're working perpendicular to the y-axis, our kind of line is going to be horizontal. Hole or no hole? Definitely hole. Again, we've got this situation. Oh, I said we were going to remedy the fact that, remember the x equals 0 when we were fighting about hole or no hole here? Notice both of the radiuses would be 0 here, so that's why they're touching, if anyone cared. Yeah, so here, everyone was concerned there would be no hole there. If you plug in x equals 0 to both of the radiuses here, they're both going to be 0. So it almost like, it's weird because you're talking about a singular point, but it kind of remedies the fact that they're touching there. At that one point, essentially you can't talk about like a singular point because then you're rotating nothing. All right, either way, here definitely hole. All right, so you should always question the man. Yeah. What? Oh, what this guy's supposed to look like? Let me see if I can. Might not be able to do it horizontally. Let me see. This might not rotate the right way. What was our graph? Square root of x? Equals 4. All right, this is gonna rotate weird, I think. So just. Yeah, so kind of very flat along the edges. That's that x equals 4 rotating around. Curvy in the middle. again, going down to that kind of singular point at the bottom, but since it's touching at the bottom, we don't really care. We want the majority of it.
Wait, so with you say polar,
We would do definitely fold.
because we're going on the left.
Yeah, you want to think. I would think like in the middle of your region. So don't really exclusively look at like the edges. Right. All right, help me out. I would love to finish at least a couple of these. So, big radius. Thoughts? 4. And I'm going to write it 4 minus 0 to do edge minus axis. But notice that is a constant radius. Remember when we looked at the picture, it looked very much like a cylinder on the outside. Cylinders have constant radiuses, so that's why that looks constant. Inner guy, what are we subtracting? That would be great if I were going in terms of x. So I do have to change this into x equals y squared. So we got to do y squared minus 0. Sorry, I kind of set you up for that one. My bad. What? All right. Let me re-explain. Top's over here, bigger x values are over there. So big radius, the bigger one. Top 4 minus axis 0. 4 minus 0.
Yes.
Bottom is this minus this. But I can't use square root of x because I've got a horizontal orientation for my line. So I have to do x equals something minus x equals something. Here, if I solve for x, we've got x equals y squared, so we've got y squared minus 0.
Yes.
All right, let's do this real quick. Factor out the pi. 16. Y squared squared y to the 4th. This one would be comfortable making you integrate. Thoughts on bounds? 0 to 2. Good. Y bounds mean, y variable means y bounds. Again, you can put your pencil on this. Here I'm going up and down to 0, up to 2. All right, let's see if we can pump out one more of these. And then we'll revisit next time. All right, x equals 4. That's this line. Polar, Mason? No. So if you have a region, the only time your bounds would change if you change the letter of the variable of integration. So if I switch between x and y, the bounds will change because I'm like going differently, but your region determines your bounds. So absolutely good notice. Hole or no hole for x equals 4? No hole. We are touching that region the entire time. Pi r squared. All right. So 1 radius. That's the spirit. All right. Top minus bottom. What are we looking at? What are we subtracting? So we don't have a hole here because we're flush up against our axis. We're just dealing with this radius. So top. What? I can put it anywhere. It won't be like this though. I like those two. I'm going to flip flop. I'm going to do 4 minus y squared. All right. Were you guys listening to Mason? Thoughts on bounds? Same? 0 to 2. Ooh, you think we can do the last one real quick? Let's just go all the way to volume, because you know what Mason told me? Mason told me that the bounds are the same, so I don't need to separate my decisions. All right, x equals 6. That's the line I drew over there through the word top. Hole or no hole? Hole. We got some space, constant amount of space too. So I'm gonna have 2 radiuses. All right, let's draw them. I like drawing the radiuses. Whee! Whee! Those little skinny orange lines. Thoughts on the big radius? Okay. All right. Axis over to the curve. Again, if you reverse that right now, it's not a big deal. Shell method, it will be. And 6 minus 4. That one makes sense there because if you think about rotating that, the middle would be cylindrical. Makes sense that it would have a constant radius. All right, before we leave, we obviously not doing a nose check because we have 2 minutes left. Announcement and all right, announcement. Actually, I most students want you to tell me what's happening at the beginning of next class.
Round two.
Round 2. If you need extra help on anything, just let me know. I'm here. And a present. Problem set. It's light. First note. Yes.
James, I must be
It's always in the top right. That's like a team group. So here, the top. Never tracking the two functions. Kind of a big difference.
So, and then when there's like, so like this one, we only have one.
No, you're good.
But then like this
Oh,
one.
okay. So you're trying to.
Okay, we got the big one minus the whole.
The odds are out of 147.
Oh, they did? Nice. Bye, guys. See you face to face around 2. Big radius first. The nice part is if you mess that up, probably, if you mess that up, you're gonna get exactly the negative answer because you will just subtract it the wrong way. So if you plug them in and get a negative answer, you'd be like, oh, weird. Bye.
Thank you.
Thank you.
You stop the recording?
No. Thank you, Brandon. Thank you.
I'm sorry, I have to write.
And you can file with your teacher, throw that in my mailbox.
Bye, Caitlin. It's always so fun. I get the first half of my day with Caitlin today. The entire first half.
Yes, ma'am.